All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to be doing more PyTorch studies. We're going to continue where we left off yesterday, and hopefully, we'll make some more progress today. So, yesterday, I was I was trying to clear up the. Oh, yeah. Okay. Sorry, I just had to look at the conversation again and figure stuff out. Off stream, I have been doing a bunch of research on, well, continuing, I should say. I've been continuing uh, doing research on various Rust related things. And one of the conversations that I've been having, one of the many conversations that I've been having with Gemini about this is one of those conversations is pertaining to CRD and TOML. So I was asking Gemini, give me a second here. Let me just. Oh, you know what? Maybe I could get Gemini to give me. Wait, where is that conversation? I can't find it. Give me a second. I'm gonna ask Gemini to wait. Okay, this is a different conversation. This is a different conversation. Sorry, I'm looking at the web UI of Gemini because due to that the whole rate limit thing with the Gemini API, for certain conversations I decided to go with the web UI. Otherwise, usually the majority of the time I use Gemini CLI, meaning I'm doing it through the terminal, which is what I prefer. So it's much easier for me to access other conversations and scroll through them and stuff like that. But in this case, I had to do it through the web UI, hopefully temporarily. Just a second. Hey, this is great info, um, and I'm gonna read it. But I was wondering if you could print out this exact answer again, but in um, raw markdown. I want to copy and paste it, paste it into a markdown file. Okay. When you write so and so, so and so, wait, is there? Um, Wait, just a second. I'm wondering if this is the entire answer. That's the code. Yeah, no, it's not. It's not doing what I'm telling it to do. Give me a second. No, I mean your entire response. Um, Present it in raw markdown such that I could copy the entire response. You want the complete full text of my previous response about so and so, so and so. Okay, this is not giving me the whole thing. Yeah, Gemini CLI does a better job of this. Well, okay. Uh, so I was asking Gemini about CRD and TOML, and how they are working together, but not exactly how they're working together. More specifically, okay, I could read out what my actual question was. Oh, yeah. So I said that, okay, I tried it out, works great, love the simplicity yet power. I'm confused about what derive, serialize, deserialize, debug. That's, I don't think I have a Rust project open here. I actually closed the other one recently. That's fine. Yeah, the that the derived statement in which serialize, deserialize, and debug are mentioned. It's an attribute. So I was asking, okay, I'm curious about what exactly this thing is doing. So Gemini replied by saying that's fantastic that you're experimenting with it. The simplicity of CRD is truly one of Rust's superpowers, but the mechanism behind it can definitely seem like magic. The so and so attribute is one of the most common pieces of Rust code you'll see, and it's a perfect example of how procedural macros work. Here's a breakdown of what that entire line is doing. Understanding derive. The derive attribute is a special is a special type of procedural macro built into the Rust compiler. Before you compile this config struct, please look at the code for the serialize, deserialize, and debug traits and write the necessary implementation for each of those traits directly onto my config struct. This saves you from manually writing hundreds of lines of repetitive code. Debug, the debug trait. Okay, I know what the debug trait does. Actually, no, you know what? I know what the debug trait does on a higher level. Oh, hold on. We seem to be losing frames. Dropping frames, rather. So let's wait until the thing stabilizes, and then I can continue talking. Okay, I think we are good. All right, so yeah, like I was saying, I know what the debug trait does on like a higher level. I know that it allows you to use the debug format specifier, format qualifier, whatever the term is there, when you're writing a print statement. Actually, okay, you know what? I could just open up a Rust project here and then show it. Yeah, let's open this. Now here we have this struct. Let me create a different struct here. So struct SO2. In here we can say A is an I32 and then B is also an I32. Now by default, I believe there isn't a way to print this struct. Give me a second, let me try and remember this whole thing. So S, this is going to be 5, this is going to be 10, and then if I try to print this, then we get, that's going to move, right? We can borrow the thing. Right. So then we get this error saying that SO2, which is the struct that I just made, it doesn't implement the display trait. The trait display is not implemented for SO2 in format strings. You may be able to use so-and-so or so-and-so for pretty printing. Okay, hold on. I never thought about the pretty printing thing. That could actually be useful. I've done pretty printing in other stuff like JSON and TOML and stuff, but within the print thing itself, I didn't know that that was an option. I need to keep that in mind because I have had situations. I have had situations where I needed to get like a nice structured printout. But yeah, okay. So the way to solve this is you could either implement the display trait to basically dictate how this struct is going to be printed out. So then you would have to implement the print method manually, or there's a certain method. I forgot what it's called, but there's a method that after you add the derived thing, I forgot how it's supposed to be, like this, I believe. Yeah, after you do this, and I think you do this as well. Hold on, where's display? I think I need to um, I think I need to add it. Oh, you know what? I don't need to do that. I could do it from here. Format, display. Where's, what? Am I missing something here? Because I'm only seeing debug. I'm not seeing display. Okay, let's try it here. Okay, display is here. Format trait for an empty form. Okay, whatever. So, display, right? Then we can, what am I missing here? What am I missing? Hold on. No, there's something I'm missing here, because you could add display there as well. Rust display. Give me a second. I'm just trying to remember this whole thing. So I'm looking at the Rust documentation. Uh, display is similar to debug. Okay, all right. Okay, implement format display. Display is a trait, isn't it? Oh, display is not a macro? Is that it? Okay, so then in that case, we wouldn't be doing this. We would instead be doing this. Implement display for SO2. That's it, right? And then we have to implement the format method, and that's where you define what exactly how this struct is supposed to be printed out, how it's supposed to be, if there's specific formatting that you like, or whatever. And if you don't want to do that, then an easier way, an easier way out is to just put the debug macro on there. That is this, and then that allows you to do something like this. Actually, I wonder if removing this would still allow me to do it. No, okay. Right, so I'm guessing the debug macro here, it handles the implementation for you. Derive macro generating, and yeah, okay. So it generates the implementation for the implementation of debug, of the debug trait on this structure. Okay, okay, all right. The debug trait is part of the standard library and is used for developer-facing output like printing to the console. What it does, it implements the debug trait for your struct, why it's needed. Without it, you cannot use the debug format specifier in your print line macros. Okay, all right. Then you have serialize. The serialize trait is the one you need for the CRD, for the CRD crate. What it does, it implements the CRD.serialize trait, which defines how your struct's data should be represented for an output format like toml, JSON, or YAML. Why it's needed. The toml.toString function requires that an input implements. Oh, that's how it's being done. Okay, okay. Yeah, because when you are creating functions, from what I remember in Rust, when you are creating functions, and this is a more like advanced concept that I looked into previously. I've kind of forgotten now how it's implemented, but I kind of remember the high level concept of it. And I'm going to be getting back into it once I continue the Rust Gemini course that I've set up. But yeah, the idea is that you can specify that a certain, like, if you are you can create a function. In the function you specify an argument, and you can specify that, okay, the argument being passed here, we don't have a concrete type for it. However, what we do know is that we want so and so trait to be implemented for this type. So whatever type is being passed, this trait must be implemented on it. And I'm guessing that's what's going on with the Toml thing. I don't remember if I have the Toml project here. I think I do. Hold on. Um, okay, let's open up Yahtzee and check here. Learning. Nope, nope, nope. Or maybe that was on a different. Maybe that was in a different project. I wonder if it was a different project. It might have been a different project. Oh, no, it was CRD. It wasn't Toml. In CRD, we're using Toml. Okay. So, in here, this is the function. Hold on, let the LSP start up and let everything load up. Now we should be able to read. Okay, so if we look over here, there, this is what I was talking about. So this is a generic function. This takes a generic input, or a reference to a generic input, and it mentions that we want whatever the input is, it must be implementing this trait. I don't remember what this plus thing does, so I can't say anything about that. Or maybe that's yet another trait that needs to be implemented, but then I don't know what the question mark is for. So I'm gonna get into that later on, once I start doing more stuff with generics plus traits, because I'm currently in the traits chapter of that Gemini Gemini Rust course. But yeah, this is what I was talking about. So I'm guessing this is how it's working, and yeah, I guess that answers my question then. Give me a second. Let's get rid of this, get rid of that. Yeah, this answers the question of what exactly serialize is doing, and how Toml is connected to serialize, how Toml is connected to CRD. It's connected in the way that CRD requires you to add the serialize and deserialize attributes to a struct that you want to be able to serialize and deserialize, right? And then whatever other crate you're using, let's say if it's JSON or Toml, or actually I think there might be JSON support out of the box. I don't remember. I don't remember. I don't wanna give wrong information, but whatever other crate you are using that is CRD compatible, you're then going to use that crate's function, which expects the input that you are giving to implement the serialize and or deserialize trait. Man, Rust is a fucking amazing language, dude. Holy shit. This is, man, that's crazy. Okay, hold on just a second. I just remembered that I forgot to open up my stream on my phone so I can see the chat. And Give me a second here. Let me just open that up and then we can continue reading. Now, before I end up getting too distracted with Rust, let's go back to this. Okay, I'm gonna read this, but before that, let me hydrate, and then I'm gonna start or continue reading this. Actually, dude, real quick, let me just check something here. Right. So we've got btop. Okay. We've got btop open here, is what I mean. And here it is showing a good like close to 2 GB, let's say. Actually, no. If we so okay, you see Firefox and you see 4 web content processes, right? All of this in total comes up to around 2.5 GB. If I open up a nano project right now, I have 6.2 GB free, but if I close down Firefox and then oh wait, shit, I forgot that btop is going to be appearing green screened on stream. Actually, I'm curious about what this looks like. Hold on, let me like go full screen or something and see what this. Yeah, it's mainly green that's missing. The green has been green screened, so it just looks very bare bones. It looks like nothing much is going on. Um, but yeah, okay. If I close this, then we're gonna save 2.5 GB. If I open up a nano project, I have to leave at least 3 to 3.5 GB for the sake of giving, an extra little window. We can say 3 to 4 GB. Okay, I would have to give about 4 GB of memory for the Rust analyzer for the nano project. After I do that, I should have some I should still have some memory remaining to uh, compile and run the nano project. Meaning we can do a tiny bit of nano development. Yeah, we can do a tiny bit of nano development. Also, I mean, to be fair, I do have like wherever you see Node in this list, Node is basically Gemini CLI because it's a Node app that's running. Um, what was I saying? Oh, yeah, dude, you know what? You know what? I'm curious if I would be able to make something like this, but for Rust. Yeah, I'm curious if I would be able to make something like this, but for Rust. It would be a little complicated because with Gemini CLI, there's a lot of like the big functionality in it, right? But it's not just the big functionality. It's okay. Hold on. Let me click away from this back here. Okay, it's not just the big functionality. It's also little things here and there, little like quality of life things, um, things that help with how do I even explain it? It's tiny little things like how it takes multi-line statements into account, or how it formats some stuff for you, how it um, There's a bunch of different things. I'm not able to think of stuff, but there's little like bells and whistles here and there in it as well. Plenty of little bells and whistles that they really add to the developer experience, or well, the user experience in this case, or well, the developer experience. Gemini CLI is supposed it's meant to be more of a code assist kind of thing. They really add to the developer experience. So I don't know if I would be able to replicate all of that. Oh shit, we are losing frames again. Okay, give it a second, give it a second. Um, hold on. Wait a minute. Okay, all right. Yeah. What was I saying? I forgot what I was saying. But my point was that okay, I could try to implement Gemini CLI using something like Ratatouille, for example. I'm curious how well that would work out because using Gemini CLI, shit, it's gonna be. Hold on, I need to check because Gemini CLI, they I need to check something. So okay, the Gemini API, they do have SDKs available in like different languages. Python is definitely one of them. Uh, I want to see if it's available in Rust because that'll make things a little more easy or a little less hectic if I don't have to worry about like the, you know, low level implementation of the requests and stuff. Rust client for Google Gemini API. A comprehensive Rust client for I think somebody made this themselves. Hold on, is this from Google or hold on? No, this is made by someone else. Um, Comprehensive Rust client library. Okay, all right. This is actively in development, which is great. That's awesome. That is great. Efficient processing of multiple requests with automatic file handling for large jobs. Oh shit, dude. They're like putting in they're oh dude. Okay. They're doing like they're putting in all of the good information in there. Even like function calling and stuff like that. So getting it to do Google searches or um, analyzing code, sending files and stuff like that. Okay. Key features. The library provides comprehensive access to all Gemini 2.5 capabilities through an intuitive Rust API. Basic content generation. All right. System prompts, multi-tone conversations, and even simple messages. Streaming responses enable real-time content streaming for interactive applications. See basic streaming, for example, so and so. Oh shit, dude. This is crazy. This is, yo, this, this is crazy. But no, I'm okay. I'm curious if there is, okay, Google API SDK, let's say. Google API libraries. Is that Google API? Gemini API SDK is what I was looking up. Give me a second here. Libraries, okay, language support and installation. It's available in, you're joking. It's available in Python, JavaScript, TypeScript, Go, and Java languages. Okay, Rust is not a part of it. Now, Rust is not a part of it. However, however, I'm wondering if there is a way that I could, because like on one hand, I could try to implement the entire like Gemini API library in Rust, but I feel like that's going to take away from what I'm trying to do because I'm trying to build higher level stuff, right? Of the languages that are supported, by the way, C Sharp is also one of them, which is good news. But yeah, of the languages that are supported, um, two of them that I'm actually very good at are Python and C Sharp. Um, I don't really want to go the C Sharp route. I'm a lot more interested in the Python route. So I need to think about how this is going to work in terms of processing. The good news is that it's the web API, right? So all of this, what do you call it? Sorry, I lost my train of thought. The good news is that this is a web API, so it's sending requests to the server. It's not doing any processing locally. So it doesn't matter if it's a Python application. To a certain extent, it doesn't matter if it's a Python application. What I would need to do is set the thing up in Python, and then have how do I say this? I would have a Rust front end and a Python back end for this. That's what I'm trying to say. I would have a Rust front end and a Python back end. This way, I would be able to focus on the more higher level stuff instead of having to focus on the low level stuff. And in this way, I would also be handling a significant amount of the the processing on the Rust side instead of on the Python side. And this would also give me an excuse to use Ratatouille. I should write this. I should write this idea down. Hold on. Let me go into my this one. Okay. Do I have something for ideas? What even was this? Oh. This actually is no longer going to be a Python script. This is going to be, I'm going to learn how to use the task scheduler. More specifically, I think it was the Tokyo task scheduler or Tokyo cron something. I don't, I think it was just Tokyo task scheduler. It's a crate that implements a task scheduler um, that is Tokyo based. So you can use Tokyo if you want. Otherwise, you can also run like a, you know, single threaded version or non-async version of it. Um, what was this? Understanding all config files and stuff, setting up a mechanism to clear all the registers. Okay, okay. Wait, why is that cut off? Oh, all right. Yeah, never mind. Um, ideas. Finish learning Lua. I think, you know what? I think at this point, I have almost finished learning Lua, and we are currently doing the back to, get back to deep learning research thing. Holy shit, we are close to like 35 minutes into the stream and we haven't started. Dude, okay. Um, to do. Do I really want to do this? Now I'm thinking because this would be like a yeah, I don't you know what? I have enough projects to do, so I don't think I'm gonna be doing this. This was great for doing research on, and if I ever do set something like this up, then I'm definitely gonna have Python as the web backend and Rust as the front end, but Rust would also be doing a bunch of processing of the data itself. So like my solution would not be nearly as good as what these people are working on with Gemini Rust. Their solution is a lot more comprehensive. It's a lot more their solution is a lot more like feature packed. It's doing things through Rust only. It's not using like a separate component. In my case, I'm using Python because there's a Python Gemini API SDK available. Um, so I'm going to be sending and receiving the requests, or yeah, sending requests and receiving responses to and from the Python side, and then that's going to be relayed to the Rust side. I am still kind of tempted to set something like this up. Yeah, yeah, I am kind of tempted to set something like this up because as hectic as it may sound, it would allow me to create another project that I was planning on working on, sort of a bot with voice capability and stuff like that. So essentially, I would be attaching a sort of voice component to Gemini. Dude, I need to stop getting distracted with this. Holy shit. Okay, we need to get back to what we are doing here. Let's continue reading this. Okay. So yesterday, after we got a pretty nice explanation about the chain rule and how the the backward how the backward function is implemented to do back propagation and calculate the gradients of the inputs. Then I asked Gemini to explain the df slash dx and df slash dy thing in a similar way. I didn't get a chance to read it because after stream I got busy doing some other research, but we can read it now. Okay, absolutely. Let's use the same conceptual approach for Yeah, let's use the same conceptual approach for so and so and so and so. The concept, isolating a single influence. Imagine you are cooking and the final taste of your dish, F, depends on two ingredients, the amount of salt, X, and the amount of spice, Y. You taste the dish and think it's not quite right. You want to know how to improve it. You have two knobs you can turn, salt and spice. The question is, which one should you turn and in which direction? This is where so and so and so and so come in. They're called partial derivatives. All right. Okay, the salt knob. This answers the question if I hold the amount of spice. Wait, so this is df and dx. Okay, if I hold the amount of spice y completely still and only adjust the salt knob a tiny bit, how will the final taste of F change? It isolates the influence of the salt. If the result is a large positive number, it means adding a bit more salt makes the dish much tastier. If the result is a large positive number, it means adding, okay, all right. Okay, so if the result is a large positive number, that means it has a big influence. It isolates the influence of the salt. Okay, so it means adding a bit more salt makes the dish much tastier. All right. Then the spice knob. This answers the question if I hold the amount of salt completely still and only adjust the amount of spice a tiny bit, how will the final taste change? It isolates the influence of the spice. Okay? The key idea is holding all the other variables constant to figure out the unique contribution of one variable you're currently looking at, of the one variable you're currently looking at. Okay. Connecting to your exercise. In your exercise, the final taste, F, was total sum. The salt was X. The spice was Y. The recipe was total sum equals this plus this dot sum. Okay, all right. When you run total sum dot backward, PyTorch calculates both partial derivatives. Wait, when you run total sum dot backward, PyTorch calculates both partial derivatives for you. It calculates tensor x dot grad, which is the partial derivative containing the sum and the tensor. Hold on, sorry, I'm trying to read it and understand it. Okay, so this is our df. So f is total sum, and then x is tensor x. To do this, it mentally freezes tensor y and treats it as a fixed component. It analyzes how total sum changes if you only wiggle the values in tensor x. As we saw in a multiplication, the influence of x is y. It calculates tensor y dot grad, which is so and so. To do this, it mentally freezes tensor x and treats it as a fixed constant. It analyzes how total sum changes if you only wiggle the values in tensor y. Unsurprisingly, the influence of y is x. So and so and so and so are not about analyzing the system all at once. They are about being a good detective, isolating each suspect or input variable one by one to determine their specific role in the outcome. Okay, all right. This is fundamental to how a neural network learns. A network has millions of knobs, its weights. After seeing a training example, it calculates the partial derivative of the error with respect to every single weight. The partial derivative of the error with respect to every single weight. This gives it a huge list of instructions like turn weight number 1 up a little, turn weight number 2 down a little, leave weight 3 alone, and so on to make the error smaller next time. Um, hold on. Okay, um, so I'm trying to under, if I'm trying to get a high level overview of um, what backward is doing without without analogies, as helpful as they were. Um, what am I trying to ask here? I guess what would be a good way to think about it? Is it that oh, I just realized what I'm trying to understand. I, because I'm trying to understand. Oh, because so far I've understood that we generate gradients and partial uh, derivative. How do you spell that? Okay, whatever. And partial derivatives. But I'm also, oh, also trying to understand how they fit together in this whole equation, let's say. I don't want to go into the math of it because again, it's calculus, and then I'm going to have to dig deeper into calculus and understand what the calculations are there. And I'm trying to avoid having to do that. So I kind of want a high level overview because so far, I mean, if we're talking about like a really high level overview, the basic idea is or the basic workflow that you follow in PyTorch, because I've done this before, so like that's why I know now. The basic idea is you run. Hold on, this thing is generating this thing, but I'll finish what I'm saying and then I'll start reading it. So the basic idea is you you have a training data set, right? So you have you have inputs and their correct outputs for those inputs, the correct outputs, right? So you are able to use this and you run the input through the neural network, and then you get the output, and then you compare the output to the expected output, as in the output that you actually got to the real output, what is the correct output, right? That gives you your loss. And then you use this loss to calculate the gradient with respect to the weights. And then that's the whole like backward process. Once you've done that, you then use the optimizer. There's an optimizer available to update the weights. That's what I know about like the higher, like really high level overview. We're probably words. We are probably gonna be holy shit. We're probably gonna be going through that whole process again, like once we get into feed forward neural networks, which is like it's like right around the corner. Okay, let's read this. Of course, let's describe it directly as a computational process. Here's a high-level, non-analogical, I have never used that word. Okay, non-analogical way to think about to think about what backward does. The backward process, a step-by-step summary. Assume you have a final single number output, a scalar. Let's call it L for loss. That was produced by a series of operations on input tensors like W and X. When you call L dot backward, you trigger the following automated procedure: initialization. The process starts at the end at L. The gradient of L with respect to itself, dl, is by definition 1. This number 1 is the initial gradient value that will be passed backward. Okay, reverse traversal. The system walks backward through the computation graph that is built during the forward pass. It visits each operation in the exact reverse order that you executed them. The core calculation at each operation. At every operation it visits, it performs one crucial calculation based on the chain rule of calculus. For any given input to that operation, it calculates the gradient to pass backward equals gradient from ahead multiplied by local partial derivative. Oh, so the partial derivative allows you to uh, change this influence. It essentially influences this gradient, this gradient value, so it can then be passed backwards. Though something that I'm curious about is how this works um, with multi-layer networks. Like where, because like okay, in this case, the gradient was only stored in our inputs, which are like at the very beginning of the computation graph. But then in a neural network, in a feed-forward neural network, you would have like multiple layers, right? And each of them stores weights, and we tune the weights of each of them, not just the first layer. Okay, let's break that down. Gradient from ahead. This is the gradient value that was passed to it from the operation closer to the final output. For the very first step, this value is 1. Local partial derivative. This is the key. Every function in PyTorch, sum, exponent, etc., has a predefined simple function for its own partial derivative. For example, for a multiplication, c equals a multiplied by b. Its local partial derivative will be, with respect to a, is just b. Its local partial derivative with respect to a is just b. So the local partial derivative of c with respect to a is b. Is that what's being said here? Okay, the backward process knows this rule. Accumulation at the leaves. This process of multiplying and passing gradients backward continues until it reaches the leaf nodes, the input tensors you created that have required grad equals true, like tensor x and tensor y in our exercise. The final gradient, the final gradient value that arrives at the leaf tensor is added to the tensor's dot grad attribute. How partial derivatives and gradients fit together. This is the most direct way to connect the terms. A partial derivative is the local calculation. It's the df dx of a single isolated function, answering what is the influence of this function's input on this function's output. Okay, PyTorch has these predefined for every operation. The gradient. The gradient is a global end-to-end result. It is the partial derivative of the final scalar output with respect to the specific input parameter. Backward computes this final global gradient by starting at the end of the chain, by starting at the end and chaining together all the simple local partial derivatives of every operation along the path. Okay, so I sort of understand how this works in our simple example where x and y are multiplied, x and y tensors are multiplied element-wise, and then summed up, and then the product is summed up. The gradient is being calculated for each of the leaf nodes. But what about a multi-layer neural? Actually, should I ask this question? Because I'm doing this course, at least according to Gemini, I don't know anything about neural networks. That's what my prompt was, right? Let me just go back and check. Hold on. How do I? Yeah. Okay, you are a tutor. You're going to teach me about feed-forward neural networks. We'll be using PyTorch as our deep learning framework, and we'll be doing coding in Python. I have the coding environment set up, and so and so. I've created so and so, so and so, so and so. I don't want to take any other. Oh, okay, that's for write operations. If anything needs to be done, okay. I would also like a small exercise and so and so. Right. Okay. I think we are good. I think we are good. Okay. So yeah. Okay. But what if we had multiple nodes in the chain? Yeah, so I'm going to ask it in a way that still kind of creates the impression that I don't know anything about feed-forward neural networks, because I want to do this so that Gemini is very much assuming that I don't know anything about feed-forward neural networks, and so the next few chapters are going to like very gently introduce me to um, well, feed-forward neural networks. But what if we had multiple nodes in the chain whose gradient we wanted to calculate? Also, should I be getting that deep into this, or is it not worth exploring right now? While this is responding, you know what? Hold on. I'm going to take a small break. We've been streaming for about an hour. I'm going to take a small break of like 2, 3 minutes. I'll be back like super quick. The response is here already, but like I'll be back in like 2 or 3 minutes. All right, I'm back. Dude, you know what I was thinking? So like in the top right of the screen, I currently have this window that I'm not really doing too much with. So I was thinking like what if I was able to come up with an idea for a working neural network that runs purely on JavaScript, or well, if I'm vibe coding it, then I'm gonna make it run purely on JavaScript. But otherwise, I could try building something in Rust. I'm not going to because I have like so much other stuff to be doing. But I was wondering like what if I set up an animation for something like that? Like I could vibe code the entire thing and um and then save those files locally, obviously. So run this then I can run that animation whenever I want. Let me see. I can try from Google AI Studio or from the Gemini CLI. No, not CLI. The Gemini web interface. Oh, you know what? Let me drop the prompt in there right now and see what Gemini comes up with in the meantime while we are streaming, because this whole thing is going to be. Oh, give me a second. Yeah, okay. Wait, what's going on here? Oh, yeah, just a second. This is going to be using. This is supposed to use Canvas. Yes, this is supposed to use Canvas. Okay, so generate generate web. What am I trying to say? Generate an animation. Generate a nice looking um, animation showing a neural network in action. Um, make it a looping animation. Um, and write the entire thing in JavaScript. Yeah, write the entire thing in JavaScript. And actually, you know what? I'm wondering if I could get it to write. I can't get it to compile this though, but I could probably get it to write Rust code to write Rust code that I can then compile to WASM. Yeah, I could try doing that. But yeah, okay. Write the entire thing in JavaScript and yeah, that's it. Write the entire thing in JavaScript. I love visualizing complex concepts like neural networks. I've created a single file HTML application that uses JavaScript and Canvas to generate a continuously looping animation. Hey, you know what? You know what? Wait, what is this? Add Gemini features? I'm not sure what that's doing. Incorporating Gemini features. Oh, stop, stop, stop. Don't do that. Don't do that. Oh God. Um, regenerate the original uh, JavaScript, please. No need for Gemini integration. Though I would need to send it from one machine to another. Okay, give me a second here. Yeah, okay. All right. Index.html. Show console, previous, refresh, changes saved. Oh, yeah, here's the code. You know what I could do? Um, I'm gonna copy this code and how would I go about doing this? Because if I copy this, yeah, how am I doing this? Oh, I probably have yeah, there's SSH, so I can use SCP to copy the file from the other machine over to this machine. I could do that. Or I could open up Yahtzee. No, no. I would still need to copy it. Yeah. Okay, let's copy from here and save. There's a much easier way to do this, but like I don't want to do that right now. Um, okay, Neo, actually, I could just do it in here. Yeah. Uh, fcnn anim dot html. Okay. Yeah, this is it. So we can close this. Right, so now there's something that I have to do on this other machine. So just give me a second. Um, I might need to, yeah, let's transition. Okay, so I need to, okay, and then we exit from here, and then, uh, do I have SCP stored here? I do. And then what are we looking at? I believe I have Yahtzee here as well, right? So here, ls, we can put it into, so there's temp Yahtzee install. Oh, what's all the, yeah, okay, I can delete it from here later on. Okay, all right. So, from here, SCP, actually, what's the IP here? Give me a second. Give me just a second. Um, right. Dude, this would have been so much simpler if I just took the other route. Especially since I'm doing this thing where never mind. Hold on. I could open up the file here and then I could copy the entire thing. I could do that. Yes, I could do that. That just occurred to me. That's crazy. Because in the Windows terminal, I can select the entire thing. That just occurred to me. Okay, temporarily, let's open up the other, okay, other laptop. And then here, we need this, and we need the entire thing copied all the way to the beginning. Okay, so let's copy that. Dude, this is something so silly that I'm spending time on right now. This is crazy. Okay, I'm hoping that that copied. So when I paste, we are not getting it. Okay. Um, if I yank, I don't think it's gonna store. Is it? Hold on. Let's see. Nope, it's not gonna store. Okay, right. Hold up. Trying to figure this out on stream is just wasting a bunch of time. So, what I'm gonna do is store it in something that I can then access somewhere else because my mind is going in like different locations. I was supposed to use SCP to the SCP CLI, the SCP tool to um, basically copy the file from one thing to another, from one machine to another. But then ifconfig was not installed, so I was thinking it was not installed on this on WSL2. So then I was like, okay, what other method could I use? And in thinking about all of these different things, I just kept on getting distracted and uh, okay. So where are we right now? Scratch stuff. That's where we are. I don't know where that folder is. Scratch stuff there. And then in here we need um what FCNN? Learning FCNN. Can I search for this? Hold up. Where is this located? Scratch stuff learning DL. Oh, also I thought I got rid of that thing. But okay. Anyways. Um anim HTML. Okay. Finish uploading that. That's done. Now we come here. Um, okay, we're good there. Just a second, just a second. I'm just doing some stuff here, and soon I will have the thing open. I'm wasting so much time on this one silly little thing, but okay, whatever. Okay, open this up. All right, done. Great. Now let me just move this tab up and bring it here. This silly little thing, I ended up spending so much time doing this, and I'm not even the one that made this. That's crazy. Um, okay, now let's go back. Okay, and I guess we are good to go. I think. Yeah, we're good to go. Okay, right. So we're gonna close this. At a later time, maybe I can generate something else from Gemini. I can think of ways to. I can probably get Gemini to generate. Um, I can probably get Gemini to generate the prompt for generating, you know, the code. Right. Close this. We're coming back here, and we're gonna now read this. Okay, both are fantastic questions that show you're thinking ahead. Let's tackle them in order. Is it worth exploring right now? For the vast majority of use cases, say 95% of the time, that's reassuring. You only care about the gradients of the leaf nodes, that is the original input tensors. Wait, really? Hold on. I thought we are tuning the weights of all the layers. Hold on. Okay. Um, the original input tensors that have requires grad equals true. In a real neural network, these are your model's learnable parameters, the weights and biases. The whole point of backpropagation is to get the gradients of these specific parameters so the optimizer can update them. Okay, all right. However, being able to inspect the gradients of intermediate nodes is a powerful debugging and analysis technique. It's like opening the hood of your car while the engine is running. You don't do it every day, but it's incredibly useful for diagnosing problems. For example, you might want to see if the gradients are becoming extremely small. Uh, that's a vanishing gradient problem at a certain point in your network. So the short answer is it's not something you'll use in every script, but knowing how to do it is a valuable skill. Since you've asked, let's do a quick demonstration. It's a perfect it's a perfect capstone to this chapter. How do we get the gradients for intermediate nodes? By default, for memory efficiency, PyTorch only saves .grad for the leaf nodes. As soon as the gradient for an intermediate node like your product tensor is used to compute the gradient for the nodes behind it, PyTorch discards it. To tell PyTorch, hey, hold on, I want to inspect the gradient for this specific intermediate tensor, you need to explicitly call the retain grad method on it. Let's modify your exercise one last time to see this in action. Okay, okay, all right. Yeah, so earlier I was trying to do this, and I remember I was getting a warning or an error or something. Where was this? Product tensor equals this and this. Okay. Actually, I think where was I trying to, well, okay, hold on. Here we can do product tensor dot retain grad, and actually let's enables this tensor to have their grad populated during backward. This is a no-op for leaf tensors. Okay, right. Then we print, what did I just type? Oh, print this product tensor dot grad, and oh, here we do product tensor dot grad. Oh, I should probably also get rid of this code here because this is going to be using up some. Okay. I mean, this is going to be using up some of the resources, and it might add like an extra 2 or 3 seconds. Okay, product tensor, so and so. Okay, cool, great. Let's see what this shows. Intermediate node. Okay, before you run it, let's predict the output from product tensor. Product tensor is the direct input to the total sum. Product tensor is a direct input to the total sum operation. Remember the rule for the sum operation. It's a simple distributor. It takes the gradient from ahead, which is 1, from total sum, and passes it back to all of its inputs. Therefore, the gradient for product tensor should be a tensor of the same shape filled with 1. Go ahead and run this. You'll see now that you'll see that you now get gradients for both the leaves and the intermediate tensor you flagged with retain grad. This officially concludes our deep dive into the mechanics of AutoGrad. You've covered concepts that many people skip over. Are you ready to move? You know what? Okay, we're gonna move on. We're gonna move on, and then I'm gonna ask this question again later on, once we do the, you know, um, once we actually um, calculate the gradients and then update the weights based on those gradients. Because I'm still curious about, because I know this, that the weights get tuned later on, and because of that tuning, we we see like a different behavior with the neural network. If the weights weren't tuned, then um, you wouldn't be seeing a change because those weights are what the input is multiplied by. Because like in a simple linear operation, it's matrix multiplication plus addition. But yeah, okay. Um, yes. Let's move on to the next thing, which is chapter 2. Wait, how many chapters did did Gemini set up? 6, up to the full training loop. Okay. Fantastic. Let's move on to chapter 2, constructing your first neural network. In this chapter, we'll take the building blocks, tensors and autograd, and start putting them together to form a feed-forward neural network. The anatomy of a feed-forward neural network. A feed-forward neural network, also known as a multi-layer perceptron, is the simplest type of artificial neural network. It's called feed-forward because information flows in only one direction from the input layer through any hidden layers to the output layer with loops or cycles, without loops or cycles. Here's its basic structure. Input layer, this is where your data enters the network. Each neuron in the layer corresponds to a feature in your input data. If you're trying to predict house prices, for example, the input layer might have neurons for square footage, number of bedrooms, zip code, etc. Okay, hidden layers. These are the intermediate layers between the input and output layers. In these layers, the network performs complex calculations to find patterns and relationships within the data. A network can have one or many hidden layers, and the number of neurons in each hidden layer is a design choice. Output layer. This layer produces the network's final prediction. For a binary classification, it might only have one neuron whose output is a probability. For a multi-class classification like cat, dog, so-and-so, it would have one neuron for each class, and for a regression task, it would typically have one neuron. Okay. Each connection between the neurons is different layer. Each connection between neurons is different layers. What? Hold on. I'm reading this all wrong. Each connection between neurons in different layers has an associated weight. What the fuck? Why was that so? Okay. Um, has an associated weight. Each connection has an associated weight. Okay. And each neuron typically has a bias. These weights and biases are the parameters that the network learns during training. Okay, building neural networks with PyTorch. PyTorch is nn.module. In PyTorch, all neural network mod in hold on, where am I? All neural network modules, layers, and the entire network itself inherit from the base class torch.nn.module. Sorry, zoned out. Okay. Um, when you build your own neural network, you will create a class that inherits from nn.module. Inside this class, you'll typically define two key things. An init method, this is where you define the layers of your network. For example, if you want a linear layer, you define self.linear, so and so. And then a forward method, this method defines how data flows through your network. It takes an input tensor X and passes it through the layers you defined in init, performing the necessary computations. This is where you connect the layers in sequence. Let's start by defining a very simple FCNN with one input layer, one hidden layer, and one output layer using nn.linear. Okay, nn.linear. This module applies a linear transformation to the input data, y equals xat. Hold on. Xat plus. Okay, I'm fortunate enough that I know. I'm, I'm fortunate enough that I know what this means. This means input multiplied by the transpose of the weights plus bias. I would have been so confused about that. It's essentially a fully connected layer with where every input neuron is connected to every output neuron in that layer. Your turn. Create a new Python file. Let's call it chapter 2 and add the following code. Okay, simple FCNN, hidden layer, output layer. Our input is going to be, okay. All right, let's do exactly that. So I can probably close this, or I could keep it open, it's fine. What I could close is probably this. Yeah, actually both of these. Okay, chapter 2.py. All right, here import torch, import torch.nn as nn. Then class simple fcnn, import from nn.module. Yeah. Okay, def init. Amazing, amazing. Okay, this is interesting though. It's passing in. Okay, super.init. In super, we seem to be passing this and this, and then we are calling init without any arguments. I can't remember if this is what we had done previously as well. Anyways, uh, hidden, no, hidden, hid, hid, hidden, yeah. Hidden layer equals nn.linear. Oh, we do have to define some parameters here. Other than self, we need input underscore size, hidden underscore size. I think that's just a number of neurons. So size is supposed to be just like an integer. It's number of input features and output features. Oh yeah, I forgot. Linear takes in features and out features and constructs the matrices based on that. Hidden size, output size. Do I need to specify the none part? I guess not, right? Maybe it might be implicit. Okay, and then dot linear, input size, and then hidden size, then self dot output layer, and then dot linear, hidden size, and output size. Okay, then forward self x. So x is going to be our input. X equals self dot hidden layer x, and then x equals self dot output layer, and finally we return x. Right. What's next? Oh, actually, let's read some of the comments. Okay. Yeah, and then contains that. Define the network class. Define the layers of our network. A linear layer maps input size features to hidden size features. Another linear layer maps hidden size features to output size features. Okay. Sorry, zoned out. Okay. Where was I? Yeah. Define the forward pass, how data flows through the network, pass input through the hidden layer, pass the output of the hidden layer through the output layer. Give me a second. Let me hydrate and then I'll continue. Okay. So input features equals 10. Hidden features equals 20. You know what? I'm going to ask Gemini to explain that math to me because I'm curious about how Gemini is going to explain it. I know how the linear transformation works, um, but I want to see how Gemini is going to explain this because in this case I'll tell Gemini that I don't mind getting into the math of this because this does not uh, involve calculus. Oh, actually, I can say if it does not involve calculus, so then Gemini doesn't know that I know about. Or maybe I'm just thinking too deep into it. Anyways, output classes equals 3. Possible output classes. Okay, all right. Then model equals simple FCNN. Input features, hidden. Oh, it's hidden neurons, not hidden features. Neurons. Hidden neurons, and then output classes. Okay. Print our FCNN model structure. Print model. Okay, then dummy underscore input torch.randn 1. What is this supposed to take? Size 1. So it's 1. Hold on, no, I'm confused about that. What? Oh, for rand n, I think we can give like a series of, so like this is a row with input features number of columns. I think that's it, right? Oh yeah, there it is. Let's say we have a batch of one data point, each with 10 features. Yeah, okay. So I forgot. Rand n takes. Hold on. Let's. The documentation can help here. Um, Size. A sequence of integers defining the shape of the output tensor can be a variable number of arguments or a collection like a list or tuple. There we go. All right. Then shape of dummy input. Okay. Shape of dummy input is dummy input dot shape. Output from the model. Did I already set this thing up for output? No, I didn't. Shape of dummy input, shape of output. Oh, that comes later on. So output equals model dummy input and print shape of output output dot shape. No, what am I missing here? Oh, maybe it doesn't know that this is going to be a tensor, and so it's not able to. Yeah. What if I because I'm assuming it's going to give. I'm assuming that's what it's going to return, right? It returns a tensor. So keeping that in mind, would I then get... Though, okay, it doesn't know that forward is being called. So then that's still not going to help. It's not going to know what the result is. Okay, whatever. I mean, I know that it's going to be a tensor. And print output from the model, print output. Oh, this didn't need to be formatted. Yeah, there's no variables to add here. So now I'm gonna run this and see the result. I also just remembered that I had like an additional thing where I was capturing extra windows. How did I set that up? I can't remember. As in, I had three windows being shown. Right now there's two terminal windows, but there I was showing three windows. I can't remember where I had set that up. I think I'd set it up by um I think I was capturing two different windows probably. I could still do that, but the problem is I don't know if OBS is going to capture both of them. I would also need to um set their placement from within Ubuntu rather than from, as in, set their placement from within OBS on Ubuntu rather than from within OBS on Windows. And then that seems like it's a little more effort than it's worth. So I kind of don't want to do that. Okay. Um, what is the result? Okay, run this and then observe the model's printed structure and especially the shape of the output tensor. This will show you how the input data is transformed through layers. Okay, let's take a look at the output. R FCNN model structure. Okay, hidden layer, output layer. Okay, then shape of dummy input is that. Okay, shape of output is that. The output is this. So the output is a bunch of probabilities. Uh, yeah. Okay. Okay. Done. Um, I would like to understand uh, the math there because you mentioned, hold on, what's the exact thing? I think it said y equals, yeah, y equals xa, what's the, yeah, t plus b, I believe. Yeah. Explain that to me, please. You also mentioned things like, hold on, there was mapping something to something. Yeah, a linear layer maps input size features to hidden size. Okay, a linear layer maps input size features to hidden size features. I haven't understood what that means. I don't mind going into the math of how all this works if there's no calculus involved in it. Okay, give me a second here. Just checking something. Yeah, okay. All right, let's just wait. Let's just wait for the response. And in the meantime, okay, excellent question. This gets to the heart of how a linear layer works. The good news is that the math involved is linear algebra, matrix multiplication. I knew that. That's why I was specifically saying, hey, if it doesn't involve calculus, then explain it to me. I wanted it to be part of this conversation because I'm going to be exporting this entire conversation to post on my own website later on. Well, whenever I do make my own website. In the meantime, all of this is just going to be well. Okay, aside from the website, it's also going to be up on GitHub. That's another thing. A bunch of these Gemini learns or Gemini teaches me conversations that I'm having. I'm going to be creating a repo on GitHub and just uploading the entire thing on there. So if anyone, you know, feels like they can benefit from it, then they can go ahead. Give me a second. There's something I remembered. Yeah, I'm just looking something up. While that is being looked up, I can. Yeah, okay. Let's break down both of your questions. Understanding maps input size features to hidden size features. Think of a feature as a single number that describes your data. In our chapter 2 example, input size 10 means each data point we feed the network. Sorry, zoned out. Okay. This means each data point we feed the network is a list of 10 numbers. Okay, all right. Hidden size. We decided that our hidden layer should represent the data using a new vector of 10 numbers. A nn.linear layer is a machine that takes a vector of a certain length and transforms it into a vector of a new length. This process of transformation is called a mapping. So nn.linear input size hidden size is a machine that maps a vector of input size to a new vector of hidden size. In our case, it converts a vector of 10 features into a vector of 20 features. This new vector is a different representation of the original data as learned by the network. The math behind the mapping. This equation design describes this equation describes how the mapping is done. Let's look at each part using the hidden layer from our example. Okay, give me a second. Wait, this is crazy, dude. I'm reading about this. So this thing is from like 2 months ago or 3 months ago or something. Um, but I recently found out about it when the story kind of resurfaced. Apparently, somebody's Google Cloud or Google Gemini API. Okay, their Gemini API key leaked on GitHub, and somehow attackers were able to use that. Apparently, this was a free tier account. At least that's what the story is saying. It was a free tier account. The API key got leaked, and then attackers used that to generate like 10,000 plus requests in 2 days. Which, if it's a free account, then how did they manage to do that? They must have been exploiting some kind of vulnerability. If that is the case, if it was a free tier account, right? Anyways, um, this student, the university student, ended up getting charged like a $55,000 bill for this. I'm still wondering if it actually was. I need to confirm whether it was a free account. Because if it was a free tier account, how was Google about to charge this student for their API key being leaked and then somebody exploiting a vulnerability in their system? And apparently, Google only wavered the charge or waived the charge um, after the internet kind of made a big deal out of this story. Otherwise, they were gonna get like 50,000 from that college student, from that university student. I need to read up more on this. Like, that's crazy. That is insane. That is okay. That's straight up scummy. If like your API key got stolen and then somebody was able to use your API key and exploit someone else's system, and then rather than them getting charged, you are getting charged because your API key was used to exploit a vulnerability in their system, which again, vulnerability in their system, that's why it got exploited, right? But then because it was your API key used, you are getting charged for it. Like, that's wild. And this is also one of the reasons why I'm like super paranoid about stuff, about just copy pasting stuff. Well, I mean, my paranoia is not because I'm going to get charged for something. My paranoia is more for, like, I don't want, my own API key to get leaked and then somebody is able to take actions on my behalf. Um, which technically that happened here as well, but like, I'm talking about like, other sorts of malicious actions. Um, well, okay, yeah, in that sense, yeah, my paranoia is the same as this person's. My paranoia is for reasons similar to this person's. Um, yeah, that's kind of why I'm also like very iffy about just dumping the entire source code of any project that I'm making onto GitHub until I've gone through the entire project and made sure that I didn't accidentally leave any API keys or any other credentials in there. Because I mean, when I'm doing coding for myself, initially I might get lazy and just for debugging purposes, I might just copy the API key in there. It's horrible practice, but like if it's just for myself and I'm not expecting to upload it later on, I'm not going to think about this stuff, right? And that's partly why I worry about these things. But that's crazy, dude. Like that kind of thing happening, holy shit. That's insane. That is crazy. But that's the thing, right? It's a free account. It's a free tier account. It's a free tier account that doesn't get charged. If it's a free tier account, then how are you getting charged for it? Because if they and you are not making like 14,000 requests in 2 days off of a free tier account. There are limitations and they get enforced. If somebody was able to do that, there was definitely a vulnerability that they exploited. I need to read up on this and get like all of the information because it's also possible that I'm just missing bits and pieces of the info. But that being said, oh, yep, okay, great. So uh, that being said, give me a second here. Okay. Hold on. Just a second. I'm looking for other people to raid, and yeah, yeah, I'm looking for other people to raid. All right, you know what? I'm gonna go to this person. Yeah, I don't know who this person is and what they're doing, but we're gonna go raid them. Their name is Ivy League Dawn, I think. I think that's what it's supposed to be. Um, it says Columbia University honors student, and they're studying. Okay, so that's gonna be it for today's stream. Um, Dude, I'm loving the progress that we are making. I'm also loving the fact that I'm streaming more regularly now. That makes me super happy. I'm incredibly happy about that. In fact, New Year's is coming up. And the thing is, on New Year's, I celebrate with my family, and um, well, there's alcohol involved. So, around the time where I would be streaming, I'm going to be super drunk. So, what I'm thinking is, what if I do a gaming stream on that day? Yeah, we could we could come up with something. I can look for like funny games to play on itch. Yeah, that would be interesting. That would be interesting. But yeah, that's gonna be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.